The James Webb Space Telescope recently captured an unexpected event involving Pluto, the dwarf planet. Pluto's peculiar orbit, which is inclined at 17 degrees and intersects with Neptune's path, brought the two celestial bodies together. This rare spectacle provides astronomers with a unique opportunity to unravel the mysteries surrounding these distant members of our solar system. Pluto was first discovered by scientists in 1930 and was initially classified as a planet. However, it was later reclassified as a dwarf planet due to its unusual orbit. Despite no longer being considered a full planet, Pluto continues to fascinate many. It features a thin atmosphere and a bright shine when near the sun. Some well-known scientists, such as Michio Kaku and Neil deGrasse Tyson, have expressed concerns that Pluto might eventually collide with Neptune. They fear that such a collision could occur in the future. Pluto is known for its unique orbit around the Sun, which takes a very long time to complete, 248 years. Having been discovered in 1930, Pluto has not yet completed its first full revolution. The appearance of Pluto from the inside remains a mystery. Pluto is the odd one out in our solar system when it comes to its orbit. Unlike other planets, Pluto's orbit is not a perfect circle, and its trajectory is steep at times. During certain periods, Pluto overtakes Neptune and approaches the Sun, which is a noteworthy occurrence. The curious crowd has been puzzled by how Pluto can continue its journey despite its unusual orbit. The reason for this lies in the different gravitational pulls that act on space objects. Pluto's orbit has been studied since it was first discovered, and scientists have tracked its complex path around the Sun. Unlike a perfect orbital plane, Pluto's trajectory is steady as it continues its journey. The motion of Pluto and Neptune around the Sun is part of what is known as the three-body problem, a cosmic puzzle where scientists try to understand the motion and interaction of celestial bodies. This problem describes the movement of Pluto, Neptune, and the Sun, along with their gravitational interactions. Computer simulations from the late 1980s classified Pluto's orbit as chaotic, meaning that small changes in its initial conditions could lead to significant deviations in its orbit over millions of years. However, despite the chaos, scientists discovered that Pluto's orbit remains stable during certain time intervals that extend beyond human comprehension. These enhanced simulations have helped scientists understand how the gravitational forces of large planets like Neptune, Jupiter, and Saturn can influence Pluto's orbit around the Sun. Neptune and Pluto are unique because they do not belong to either the inner or outer solar system. The phenomenon of abytal libration explains how Pluto always remains at least 90 degrees away from Neptune when it crosses Neptune's orbit. Additionally, the deviation of Pluto's orbit from the ecliptic plane is known as latitude libration, which is why Pluto's orbit is so high above the ecliptic. Pluto only gets close to Neptune or other large planets when it is near them. Pluto is also described as having two sides, a soft one and a hard one, which complement each other and offer protection. Scientists using computer simulations discovered that the greatest deviation in Pluto's orbit from Neptune occurs every 300 years, due to a 3-on-2 orbital resonance. This resonance means that Pluto orbits the Sun twice for every 3 orbits Neptune makes. The gravitational pull of the Sun helps straighten Pluto's orbit over time. Jupiter and Saturn also influence Pluto's orbit. Jupiter's gravity plays a significant role in keeping Pluto's orbit stable, while Saturn contributes to the small ring system next to Jupiter's. These tests reveal that Pluto can maintain a relatively stable orbit over billions of years, thanks to the gravitational forces exerted by these larger planets. Without such forces, the cosmic order would be disrupted, and the system would become unstable. If two bodies in space were to collide or move out of their path, it could lead to chaos in the cosmos, as can be observed with Pluto. Predicting celestial events, especially those involving planets with irregular orbits like Pluto, is inherently difficult. The forecast of such systems is unpredictable, which is why long-term predictions are avoided. While Pluto has one of the most unstable orbits, it is still a crucial point of interest for scientists. It serves as a reminder of how the universe is constantly changing. Some scientists, who have staked their reputations on the possibility of a Pluto-Neptune collision, admit that while their relationship is intricate, a collision could still occur. This idea prompts the question of whether a collision between these two celestial bodies is even possible. Neil deGrasse Tyson, a well-known scientist and advocate for space exploration, has provided insight into the secrets of our solar system and played a key role in Pluto's reclassification. Tyson views Pluto's orbit as an example of the vastness of space yet to be explored. He believes that Pluto's peculiar orbit contributes to the allure of astronomy and sparks curiosity about the universe. Tyson warns the public about the potential dangers of Pluto's unusual orbit. A collision between Pluto and Neptune would likely create a super shockwave, which could slightly heat Pluto's surface. Due to Pluto's small size and partially frozen state, the collision could release a huge amount of energy. Material from the impact could be ejected into the outer reaches of the solar system, potentially affecting neighboring planets and their moons. However, the immediate impact on Earth would be minimal, as the outer solar system is relatively far from our planet. The scientific implications of such a collision, however, would be massive. A powerful telescope could even temporarily increase Neptune's brightness to the point where it could be seen with the naked eye from Earth, appearing as a dim star. Similarly, physicist Michio Kaku described how the event could be connected to his ideas about the universe. He believes that a collision between Pluto and Neptune would be an astrophysical event, something that might only happen once or a few times in the history of the universe. Such events challenge our understanding of string theory and the vastness of space. In comparison, the TRAPPIST-1 system, a group of 7 Earth-sized planets, follows patterns due to their gravitational interactions. While these planets could potentially collide, their orbits prevent any crashes for now. Scientists continue to monitor these planets closely, studying how their movements influence one another as they get closer. The vast distances between stars and the rarity of multiple planets being visible in the sky make such crashes unlikely. The TRAPPIST-1 system serves as a cosmic display, where the planets spin and interact, offering us new insights into the wonders of the universe. It is a reminder of how fascinating and mysterious space can be. The study of Pluto's orbit and its interaction with other celestial bodies in the solar system is not only crucial for understanding the dynamics of our local cosmic neighborhood, but also offers insights into broader astrophysical principles. While Pluto's orbit is often considered chaotic, scientists have made significant strides in understanding how such chaotic orbits can still exhibit periods of stability. One key to this stability lies in the orbital resonance between Pluto and Neptune. This resonance ensures that although the two planets' orbits cross, they never actually collide due to the precise alignment of their movements, which prevents close encounters despite the apparent chaos. The phenomenon of orbital resonance, specifically the 3:2 resonance between Pluto and Neptune, is a fascinating aspect of planetary dynamics. This resonance means that for every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This relationship ensures that Pluto and Neptune will never be in the same position at the same time, even though their orbits intersect. The gravitational influence of Neptune on Pluto is considerable, but it is precisely the resonance that keeps Pluto's orbit from destabilizing. This kind of gravitational dance is a common feature in many areas of the solar system, where the gravitational influence of one body helps to maintain the orbital integrity of another. However, the interactions between celestial bodies like Pluto, Neptune, and the Sun are not limited to simple orbital mechanics. The vast distances between planets and their complex gravitational interactions lead to a variety of phenomena that are still not fully understood. One such phenomenon is the unusual orbit of the dwarf planet Eris, another member of the distant solar system that is sometimes compared to Pluto. Eris's orbit is even more eccentric than Pluto's, and studying its motion could provide more clues about the gravitational forces that govern the outskirts of the solar system. As astronomers continue to observe Eris and other trans-Neptunian objects, the similarities and differences between these distant worlds and Pluto may yield new revelations about the formation and evolution of our solar system. Another important aspect of studying Pluto is its role as a representative of the Kuiper Belt, a vast region of space beyond Neptune that contains numerous small icy bodies. The Kuiper Belt is home to many dwarf planets, comets, and other objects, and its study has become increasingly important in our understanding of the outer solar system. Pluto is one of the largest known objects in the Kuiper Belt, and by examining it, scientists gain insight into the conditions and processes that occurred during the early days of the solar system. The Kuiper Belt is thought to be a remnant from the solar system's formation, containing material that never coalesced into full-fledged planets. The study of Pluto and the Kuiper Belt also opens up the possibility of studying other solar systems that may harbor similar regions of icy bodies. These distant regions of space may contain clues about the formation of planetary systems around other stars. As telescopes like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory continue to observe distant star systems, astronomers hope to detect exoplanets and exokuiper belts that could reveal patterns similar to those in our own solar system. The study of these distant worlds could help scientists understand how planetary systems evolve over time and how they may differ from the structure of our own solar system. In addition to their role in planetary science, objects like Pluto are also crucial for understanding the conditions that might support life. While Pluto itself is far too cold and inhospitable for life as we know it, the study of its atmosphere and surface conditions can inform our understanding of how planets and moons in other solar systems might develop the necessary conditions for life. For example, some moons in the outer solar system, such as Europa and Enceladus, are believed to harbor subsurface oceans that may offer environments suitable for life. Understanding the physical and chemical processes at work on Pluto could help scientists identify similar processes occurring on these other bodies. As technology advances, the tools available to study distant objects like Pluto continue to improve. The James Webb Space Telescope, which is already sending back incredible images and data, is expected to provide even more detailed observations of Pluto and other distant objects in the Kuiper Belt. This next-generation telescope will allow scientists to observe these objects in infrared, revealing new aspects of their composition and behavior. In the coming years, Webb's observations may also help resolve some of the outstanding questions about Pluto's atmosphere, surface features, and the potential for a collision with Neptune. One intriguing aspect of Pluto is its seasonal changes. Although it takes 248 years for Pluto to complete one orbit around the Sun, this long orbital period means that Pluto experiences seasons that last for decades. These seasonal changes have a profound effect on Pluto's atmosphere, which is made up primarily of nitrogen, methane, and carbon monoxide. As Pluto moves closer to the Sun during its orbit, the increased heat causes its atmosphere to expand. When it moves farther away, the atmosphere condenses and freezes, with some of its gases falling to the surface as ice. This cycle of atmospheric expansion and contraction provides valuable data for scientists studying the behavior of atmospheres on other icy bodies in the outer solar system. The exploration of Pluto also highlights the importance of spacecraft missions in expanding our knowledge of distant worlds. The New Horizons mission, which flew by Pluto in 2015, provided the first close-up images of the dwarf planet and its moons. The mission also captured data about Pluto's surface features, including vast plains of frozen nitrogen, towering mountains, and deep valleys. New Horizons also revealed that Pluto has a complex and diverse surface, with areas of both ancient and young terrain. These findings have challenged our understanding of the geological processes at work on Pluto, suggesting that the dwarf planet is still geologically active in some regions, despite its small size and distance from the Sun. In the broader context of space exploration, missions to distant objects like Pluto inspire a sense of wonder and curiosity that drives public interest in science. The dramatic images sent back by New Horizons, combined with the insights gained from other telescopic observations, have captivated the imagination of people around the world. These discoveries remind us of how much we still have to learn about our own solar system and the wider universe. As we continue to study Pluto, Neptune, and the distant regions of the solar system, we are not only gaining a deeper understanding of our cosmic neighborhood, but also learning about the fundamental forces that shape the universe. The continued study of Pluto's orbit and its interaction with Neptune serves as a reminder of the complexity and dynamism of our solar system. Although Pluto's fate remains uncertain, its role as a symbol of scientific curiosity and exploration will continue to inspire future generations of astronomers and space enthusiasts. With each new discovery, we inch closer to unraveling the mysteries of the universe, one distant planet at a time. In addition to the scientific advancements made through studying Pluto, there are broader philosophical and societal implications that arise from our exploration of distant celestial objects. As we continue to probe the outer reaches of the solar system and beyond, we are reminded of the vastness of the universe and humanity's place within it. The exploration of objects like Pluto challenges our perspective, encouraging us to think beyond Earth and appreciate the complexity of the cosmos. This shift in thinking can inspire new avenues for scientific research, as well as a renewed sense of wonder and curiosity that can unite people across cultures and disciplines. Pluto's reclassification from planet to dwarf planet also highlights the evolving nature of scientific understanding. The decision was based on updated criteria for what constitutes a planet, which were formulated as our knowledge of the solar system grew. As astronomers discover more about distant worlds, these definitions and classifications may continue to evolve. New discoveries, such as the detection of rogue planets or exoplanets in distant star systems, may prompt further revisions to our current models of planetary science. The dynamic nature of scientific knowledge is an important aspect of the ongoing quest for understanding, as new data often leads to refined or completely reimagined theories. Moreover, the study of Pluto and other celestial objects has practical applications. For instance, the development of technologies used to study distant planets, such as the advanced imaging systems in the James Webb Space Telescope, has led to innovations in various fields, including telecommunications, medical imaging, and materials science. The scientific instruments designed for space exploration often have far-reaching applications beyond their original purpose, benefiting industries and improving the quality of life on Earth. Looking ahead, as humanity contemplates space exploration beyond the solar system, Pluto's story will likely remain an enduring symbol of our drive to explore the unknown. Whether through robotic missions, telescopic observations, or future manned space expeditions, the journey into the cosmos continues, and the mysteries of Pluto will undoubtedly inspire generations to come.